In this video, we'll talk about the derivative rules for exponential functions. The exponential rule tells us that if you compute the derivative of e to the x, you get e to the x. In other words, the derivative of e to the x is itself. So this is the exponential rule, and the question is, can we prove it? To prove the exponential rule, we recall that e is the unique base of an exponential such that the tangent line at the point 0, 1 has slope 1. All exponentials of the form a to the x pass through the point 0, 1, but e to the x is the only one for which the tangent line there has slope 1. The curve drawn here in blue is the graph of y equals e to the x. The other graphs belong to exponentials with different bases. This is 2 to the x, and 3 to the x, and 4 to the x. All of these graphs pass through the point 0, 1, and indeed if we were to draw in y equals a to the x for any base, it would pass through this point. And every one of these curves has a tangent line at the point 0, 1. But the only one of these that has a tangent line with slope 1 is the exponential with base e. So if we were to draw in a line through the point 0, 1 that had slope 1, it would be tangent to y equals e to the x, right there. And e is the unique base for an exponential for which the tangent line at 0, 1 has slope 1. This might not seem like that important of a property, but it turns out to be exactly what we need. And we can see that if we try to prove this theorem. So how are we going to prove it? Well, let's divide it up into two steps. For step 1, we look at the function f at x equals e to the x, as you can see here. Now we already know that f prime of 0 is 1. That's what we were just talking about. The slope of the tangent line when x is equal to 0 is 1. But what happens if we try to compute this value using the limit definition of the derivative? We start with f prime of 0 is equal to the limit as h approaches 0 of the difference quotient, f at 0 plus h minus f at 0 divided by h. Well, remember, f at x is e to the x. So f at 0 plus h, that's just f at h, which is e to the h. And what about this term, f at 0? Well, e to the 0 is 1, so that's just a 1. And we still have an h in the denominator. But we know that f prime of 0 is equal to 1, so that tells us that this limit as h approaches 0 of e to the h minus 1 over h is equal to 1. It might not be clear why that's important, but it turns out that that is exactly the limit that we'll need to compute. Let's move on to step 2. So for step 2 of the proof, we're going to compute f prime of x for arbitrary x, and we're going to do it using the limit definition. So we'll start by writing f prime of x is equal to the limit as h goes to 0 of the usual difference quotient, f at x plus h minus f at x over h. Now let's not forget what f is. F at x is e to the x. So this is going to be the limit as h approaches 0 of e to the x plus h minus e to the x over h. Now what I'm going to do is I'm going to just rewrite this first term slightly. Instead of writing it as e to the x plus h, I'm going to write it as e to the x times e to the h. Subtract e to the x over h. So this is our term here. Remember that exponentials having the same base, when multiplied together, have the effect of adding the exponents. Okay, so what's the point of that? Well, notice that we have an e to the x here and an e to the x there. So I'm going to factor out that e to the x. So we'll have the limit as h goes to 0 of e to the x times e to the h, that's supposed to be an h, minus 1 over h. And here's our e to the x right there. Okay, well, what is e to the x? It's some number. Now, we don't know what x is. X is an arbitrary number, but it's just some number. And it doesn't depend on this limit. This limit, as h goes to 0, affects things that have h in them. Here's an h, here's an h. There's no h here. This e to the x term, this is constant with respect to this limit. The limit is asking what's happening as h goes to 0, but that doesn't change e to the x. E to the x is just sitting here unchanged. So we can take it outside of the limit. So then this becomes e to the x times the limit as h goes to 0 of e to the h minus 1 over h. So here's our e to the x again. And then we look at that limit for a minute. The limit as h approaches 0 of e to the h minus 1 over h. And we think, hang on, that looks familiar. If we go back to the previous slide, we can see that this is exactly the limit that we had. The limit as h goes to 0 of e to the h minus 1 over h. E to the h minus 1 over h. So we know that this quantity is equal to 1. So we have that this is equal to e to the x times 1, which of course is just e to the x. So if f at x is equal to e to the x, then f prime of x is equal to e to the x, the same thing, which we can also write as the derivative with respect to x of e to the x equals e to the x. And that's our exponential rule. Now, in fact, the reason e to the x has itself as its derivative is because of how we defined it. We defined e to the x to be the exponential having the base that its derivative at the point x equals 0 is equal to 1. And that's precisely what we needed right here. We needed to know that the derivative at 0 was equal to 1, because that's exactly what this limit is. This limit is the derivative at x equals 0. So by our choice of definition for e, we're able to ensure that the derivative of e to the x is e to the x. So as an example, let's find an equation of the tangent line to y equals e to the x plus 3, where x is equal to 2. Okay, so as usual, when we're finding the equation for a line, we need a point and a slope. Well, for the point, we're already given the x-coordinate. The x-coordinate is x equals 2. And the y-coordinate is e to the 2 plus 3, which is e to the 5. So that means our point is 2 comma e to the 5. Okay, now in order to get the slope, we need to define a function. And that function is going to be f at x equals e to the x plus 3. So then the slope at any given x is going to be the derivative at that x. So f prime of x is equal to, well, it's going to be the derivative with respect to x of e to the x plus 3. Now this isn't e to the x, it's e to the x plus something, so we're going to have to modify it a little bit. So we're just going to rewrite it. So this is the derivative with respect to x of e to the x times e to the 3. So again, we're using the fact that if you multiply two exponentials with the same base, that's the same as adding the exponents. So now we have a constant here. This is e to the x times e to the 3, but e to the 3 is a constant. So e to the 3, that's a constant. So we can just take it out. So this is e to the 3 times the derivative with respect to x of e to the x. But of course, the derivative of e to the x with respect to x is e to the x. So f prime of x is equal to e to the 3 times e to the x, which is actually the same as e to the x plus 3. So it turns out that the derivative of e to the x plus 3 is also e to the x plus 3. Now what we're interested in is the case where x is equal to 2. So that's f prime at 2 is equal to e to the 2 plus 3, which is e to the 5, which was also our y value for our point. Okay, so now we have everything that we need. So the equation of the tangent line is going to be y minus the y value is equal to m times x minus the x value. And that's the equation of our tangent line. There's a slightly more general version of the exponential rule, which states that the derivative with respect to x of e to the kx is equal to k times e to the kx, where k is some constant. So how are we going to go about showing this? Well, basically we do it the same way. It just requires a little bit of a tweak. So let's let f at x be equal to e to the kx. And we want to compute the derivative. So f prime of x is equal to the limit as h goes to 0 of what? Well, this is going to be equal to f at x plus h minus f at x divided by h. And this will be equal to the limit as h goes to 0 of f at x plus h. So in this case, we just want to be a little bit careful. Whatever the input is, so if x is the input, it's e to the k times that input. So now our input is x plus h. So we're going to take k and multiply it by the entire input, everything in the input. So this is going to be e to the k times the input, x plus h. And then it's minus e to the kx divided by h. So our entire input is x plus h. So all of that input, everything in the input is multiplied by k, and then we do e to the k times the input. So what are we going to do now? Well, the first step is to distribute that k into the x plus h. So we'll rewrite this as the limit as h goes to 0 of e to the kx plus kh minus e to the kx over h. Now this should look slightly familiar because what we're going to do now is we're going to do something very much like what we did before. We're going to factor out an e to the k times x. So the first thing we need to do is just slightly rewrite our numerator. So we're going to write this as e to the kx times e to the kh minus e to the kx over h. And now you can see that we have a common factor of e to the kx. So we can factor that out. So it's the limit as h goes to 0 of e to the kx times e to the kh minus 1 over h. And again, we have something here, e to the kx, which doesn't have any h's in it, so we can take it out of the limit. So this is e to the kx times the limit as h goes to 0 of e to the kh minus 1 over h. And now we just have to be a little bit careful, because this isn't exactly the same limit that we were looking at before. It's not the limit as h goes to 0 of e to the h, it's now e to the kh. So we're going to do a little algebraic trick. What we're going to do is we're just going to multiply by a k down here. But of course, if you put one in the denominator, you have to put it in the numerator as well. So we're going to multiply by k. And now what I'm going to do is just rewrite this a little bit. So this will be equal to the limit as h goes to 0. And what I'm going to do is I'm going to factor this k out. Again, this k has nothing to do with h. So I'm going to take this k right here, and I'm just going to take it outside of the limit and put it there. So the first thing I need to do is just erase that and write this as e to the kx times k times the limit as h goes to 0 of e to the kh minus 1 over kh. And now what we notice is that we have a kh in the exponential and a kh in the denominator. Now k is just some constant. So as h is going to 0, kh is also going to 0. Let me just make a little bit of a substitution here. So what I want to do is I want to write let u equal k times h. Then u goes to 0 when h goes to 0. So why is this helpful at all? So this becomes e to the kx times k times the limit. Well, instead of h going to 0, I'm going to write this as u goes to 0. E to the u minus 1 over u. And notice that this limit is exactly the same as our original limit from several slides ago. It's just instead of having an h here, it's a u. But we have u going to 0 of e to the u minus 1 over u. So this is exactly the same. So this is going to be a 1. So this value right here is going to be 1. So we're going to have e to the k times x times k times 1, which we can just rewrite as k times e to the kx. And this was what we claimed. The derivative of e to the k times x is k times e to the kx. So when you differentiate e to the kx, the constant k comes down. Okay, let's use this to prove another general exponential rule. Now this actually is the same thing, even though it doesn't quite look like it. So we have the derivative with respect to x of a to the x is equal to a to the x times ln of a. So here we're assuming that a is a positive constant. So a is a positive constant. Okay, so how's this going to work? So here's the key fact. A is equal to e to the ln of a. We know that this is true because e is the inverse of ln, so they cancel each other. This is just the cancellation laws telling us that e to the ln of a gives us a. So how are we going to use this fact? Well, a to the x is equal to e to the ln of a raised to the x. But if you have an exponential that you raise to an exponent, you multiply the exponents together. So it's going to be e times ln of a times x. Now this is exactly our e to the kx, where we have that k is ln of a. So if we want to differentiate a to the x, that's the same thing as differentiating e to the ln of a times x. Which again, this is just the same thing as the derivative with respect to x of e to the kx for this particular choice of k. So k is equal to ln of x. Or excuse me, k is equal to ln of a. So then we just use our rule from that we just proved. So this is k times e to the kx, but k is ln of a. So this is k times e to the ln of a times x. And now we're basically done because now we just remind ourselves that e to the ln of ax, this thing right here, is the same as a to the x. So this quantity, right, e to the ln of ax, that's this thing right here, that's the same as a to the x. So this, all of this stuff that we've highlighted here, that's a to the x. But what was k? Let's not forget what k was. K was ln of a. So this k, that k there, that's ln of a. So the derivative with respect to x of a to the x is equal to ln of a times a to the x. Or if you want to rewrite it, a to the x times ln of a. And this allows us to differentiate a to the x for any base. As an example, let's find an equation for the tangent line to y equals 2 to the x at the point 1, 2. So, as usual, we need a point and a slope. Well, the point is given to us. The point is 1, 2. And so we need the slope. So the slope is going to be given by the derivative. So the slope is going to be m is the derivative with respect to x of 2 to the x evaluated at x equals 1, because that's the x-coordinate we're given. So what is the derivative of 2 to the x? Well, that's going to be 2 to the x again times the natural logarithm of 2. And we want to evaluate this at x equals 1. So you just take this x equals 1, and anywhere you see an x, you just plug in x equals 1 right there. So we'll just have 2 to the 1 times ln of 2. So our slope is 2 ln of 2. So that means that the equation of our tangent line is y minus the y-coordinate equals the slope, 2 ln of 2, times x minus the x-coordinate. And that's the equation of our tangent line. Let's compute dy dx, or the derivative of y with respect to x, if y is equal to e to the negative x plus x to the e plus e to the e. Well, this is a sum of three terms, and we can differentiate them term by term. dy dx is the derivative with respect to x of all of these terms, e to the negative x plus x to the e plus e to the e. And we want to differentiate term by term. So that's the derivative with respect to x of e to the negative x plus the derivative with respect to x of x to the e plus the derivative with respect to x of e to the e. All right, so let's just make a couple of notes here. So this first one, we use the exponential rule. E to the negative x. So we're going to use the more general version of the exponential rule. Here we have x raised to a power. So here we're going to use the power rule. And here we have e to the e. E is a constant, and we're raising it to e, which is a constant. So this is just a constant, so we're going to use the constant rule. Okay, so with that in mind, dy dx is equal to the derivative of e to the negative x is going to be negative e to the negative x plus, and now we use the power rule, so the exponent comes down, then it's x raised to the e, and we lower the exponent by 1, plus, and the derivative of a constant is 0. Therefore, dy dx is equal to negative e to the negative x plus e times x to the e minus 1. And that's our answer. Let's talk about something a little more complicated. We know how to compute the derivative of a power function, x to the p, where p is a constant. And we know how to compute the derivative of an exponential function, a to the x, where a is a constant. Well, specifically, a is a positive number, and we usually don't want a to be equal to 1. Now, the real question is, how do we compute the derivative of something like x to the x? Computing this directly using the limit definition will be a considerable challenge. So instead of doing it that way, using the limit definition, we're going to develop some additional tools that will help us with the computation.